what we discussed last time was this simple idea that in order to understand the universe and the world, a small number of things are required. And we discussed some of them. So the things required we listed were the equality sign, units, so we discussed the idea of equality, and we discussed the unit L when we introduced geometry. Now we come to the star of this whole business, and that is the unknown. Now, this unknown x is a term used to describe not just one variable x which is unknown, but many, many other possibilities. It is just a shorthand to say that when we try to understand a particular phenomena or to model some event, then we make use of symbols. And the symbols will have, so this thing, the unknown, and it also introduce symbols. Right? So let me start by giving a simple example. Suppose a rich person is given a box, beautiful box, and he knows the weight of the box. So we have a box, as soon as I've said that, I have introduced the unit of mass, right? So we had length before when we were talking about areas and land. Now we come to the next stage, which is the weight of something. Now you have to choose a certain unit. It could be grams, it could be kilograms, it could be thousands of kilograms. In certain parts of the world, they use things called pounds. So all of these things are ways in which the weight is measured. Now, once the weight is known of the box, we use a symbol. And we use the symbol W0. That is the weight of the empty box. So the 0 indicates there's nothing in the box. Now the box is locked when it comes to this particular person, and the box contains gold coins. You see, this is to increase interest. You see, if I had said it has some pieces of paper in it, then it would not be so interesting. But it has a certain number of gold coins. And the number of coins the number is not known, okay? But weight of single coin known. I again use a symbol, right? So I've used two symbols, right? The advantage of using a symbol is that it allows me to deal with the infinite number of possibilities. Each case, I have to pick a certain number for W0 and a certain number for this. But by using the symbol, I include all of these cases in the one shot. And that is the power of the symbol. It allows you to deal with a huge number of cases in one shot. Now what you do then is you weigh box with coins. Right? Again a symbol, and you weigh the box with the coins and you get W. So now we have information which is based on measurement. Right? And once this information, there is an unknown, which is the number of coins is not known. We introduce a symbol n. So we have the empty box W0, the box with the coins is W, the weight of a single golden coin is G, and we want to find out how many coins are in the box without opening it. So to do this, we use an equation. So you have an equation. And the equation is the n into G plus, right? So this is the empty box, this is the weight of the unknown n, G, and that's the weight you get. So what you do then is you subtract W0 from both sides. So this is a balance, this and this balance. By subtracting, the balance is maintained, and so you get n G is the W minus W0, and divide both sides by n. Right. So here you see we have solved a problem to find something which we couldn't open the box, but even without opening the box. So this is a very simple example of a general procedure for finding something which you don't know. Now, when this kind of thing is taught, sometimes the students have a problem. I had a good friend called Peter Tierney, and he taught in a school in Dublin, and he had posed a problem to the students in his school. And this was an area in which the students were not really, it was not a very affluent area. And the problem he said was a certain number of adults, 5 adults and 3 children go to a cinema. The price of the ticket they pay with a certain amount. If 2 adults and 1 child go, the price of the ticket is so much. Find out the price of adult ticket and the price of a child's ticket. So you had equation like this. So you have n1 adults, adult ticket is A, plus n child ticket, adult is C, is equal to P1, and then you have n2 A plus nc2 P2. Right? So from this you are supposed to find right? As soon as he said this problem with numbers, one student stood up and he said, "Mr. Peter Tierney, sir, this is a silly problem." As soon as you enter, he said, the cinema hall, it clearly says adult so much, child so much. What is the point? What is the point of complicating the thing? And he was dead right. You see? So the problem which one considers should be something where you genuinely find something out, and the thing you find out should be of interest to the people. So those are some rules which one should remember in explaining any phenomena, anything. Now it turns out that there was a problem in the House of Commons when some members of Parliament stood up and said in school they had to learn a thing called the quadratic equation. And never in their life had they ever had to use the quadratic equation. It was a silly waste of time. And this is in the proceedings of the House of Commons. Then the House of Lords in England came back and said, no, the quadratic equation is the foundation of civilization. And the reason for that was civilization nowadays depends having a government, and the government runs the country based on tax. They get taxed income. So the first quadratic equation was suggested by the Babylonians, who had a land tax. And suppose a certain person has to pay tax T, that's a tax, and you set aside a certain area of land. Whatever you grow, you have to pay the tax. So you're told you pay tax T. And then you set aside some land, a square piece of land, which is area x squared. And for this piece of land, you pay tax T. So you know the amount of tax, and there's a constant here. Right? So per unit area, you say percent tax. So if you have an area x squared, you pay tax cx squared, which is T. You see, so to solve this problem, this is a quadratic equation. Right? And so for this reason, and if you want to read this, there's a thing called Hansard, and there are proceedings of the House of Lords, and there this particular discussion is recorded. So you see that there is always a conflict between what one learns routinely and the world outside. And very often, unless it is clear why you are learning something, then the motivation for many students is not there. Some very good students who sit in the front, they will be doing all the problems, and they will not bother why they're doing it, because the adults know best and they're following the rules. But there are many others who are involved with outside activities. They go out and earn money for their family, and they do various other things, and for them it seems to be a waste of time sitting here learning things which are of no use. So the interest can be created in many different ways, one by realistic problems, and the other a vision that these abstract symbols are allowing you to probe into the universe. You're finding things about how big is the universe, what is the mass of the sun, what is the mass of the earth, and all of these things are of interest to human beings. We all rejoice when we hear that someone in the world has solved a certain problem, like Fermat's problem. It is not going to affect my life at all, whether Fermat's problem is solved or not solved, but we all rejoice. When people first learned that the earth is round and a certain radius, everyone was delighted, because when you do any one of these things, you suddenly have a different picture of the universe and of the world. And according to quantum theory, when that happens, there is a transformation to you and to the universe. So this is a great idea which is actually based on these physics principles. So once we have symbols, you can see that this is confusing for people who are thinking very concretely. But once you begin to understand the power, which I repeat, is that in one shot, an infinite number of problems have been solved. So now we go to the next step of abstraction. and that is, instead of dealing with one unknown x, we introduce the extraordinarily powerful idea of a function. So f. So let me, you see, in these examples, I have called the unknown x, but then I deliberately kept changing. I've called the unknown n, I've called the unknown g, different symbols are used, right? But we've clearly specified that there is an unknown. So here again, let me start with a simple example, s of n, which I can write as s of n, like this, and which is equal to 1 plus half right. So this thing is you're adding what is a geometric series, right? And it stops after n terms. So each time I change n, this number changes. So this is a function of n. This number Sn changes when n changes. So what we have is the notion of a function, and this thing we know is 1 minus half to the power of n plus 1 divided by 1 minus half. Right? So this is a very simple example of a function, and this function we will use as an example later on. Right? For the moment, it is very clear that this notion of function is all around us. Suppose we want to look at the temperature. So the temperature in Chennai in the morning is a certain value. In the afternoon, it's a certain value. At night, it's a certain value. So what you have is a function. You have temperature versus time. So as soon as I've done that, I've introduced another unit. So let me have this example then, that you have temperature T as function so write T of T, right? And so you need right. So these very, very simple examples are everyday examples. This is an abstract example, but this is an everyday example. If you have something moving and changing with time, that would be position of Earth with respect to the Sun. So will be x Earth T. Right? So you may need more than one variable, but you get the idea that this is something which changes with time. So the idea of a function is a very, very powerful idea. So once you have the idea of a function, then you can start looking at the world, looking at events, and trying to describe them in a mathematical way. And when you use the mathematics, then you have to use units to introduce numbers. So for applications, the idea of a unit is absolutely fundamental. And without the units, you cannot convert what you are observing into something which can be given a numerical value. So the units have to be such that anyone in the world, anywhere, will be using the same units. So something which is done in India or something which is done in America or in England or in Japan, when they're making a measurement, they're using the same unit of measurement. So there are international commissions who decide on the units to be chosen, and there is agreement usually. But for example, there is no agreement between most of the world and the US. The US use a system of units like feet and yards and miles. The rest, most of the world has converted to centimeters and meters and so on, and grams, right? So there are different systems of units, so you must know how to convert from one unit to the other. So in other words, to do any practical problem, you have to choose a unit. And once you choose a unit, you get an answer which is in a certain unit. But you should be able to change from one unit to the other. And the rule for doing that should be straightforward. So that is all I have to say about this kind of thing. But I hope it's very clear that this opens up the possibility of modeling. It opens up the possibility of trying to explain what has happened in a way which is quantitative, not qualitative. So let us now move on to use the power of algebra in geometry. Right? Okay, so what we will do is we look at two dimensions. And in two dimensions, we choose an origin like this, and this we call the x-axis, and this we call the y-axis. And we choose a unit here, and we choose a unit there. So once we've done that, and this is 90 degrees. So we have two lines. These are number lines. So we can put numbers here. So this would be plus, this would be minus 1, this would be minus 1, right? And so if I choose a certain point here, then this particular point will have a certain value like this. This is y, and a certain right. So to get to this point, we move along this by so much x units, and we move up by this units and y, and I write x and y. Right. So by this one step, what we've done is we have started describing points using algebra, using symbols. Right? We're not just drawing pictures, but now we have got a symbol, and so we can say this is 1 inch and this is 2 inches. This could be 5 inches and 3 inches. So each time we do that, we get a different point. But there's more, because now we know the distance from here to here, distance from this point and the point P, this distance, if I call that r, the distance, then the distance r squared is x squared plus y squared from so Pythagoras' theorem tells you that this is a right angle triangle. These are the two sides of the right angle, and this is the hypotenuse, and the square of the hypotenuse we showed is given by this. So by this we have a notion of distance which is precise and mathematical, written in terms of symbols. Now this was an enormous step. So things which were where pictures were used, can now be converted into algebraic statements. So I will just give one example. Suppose we have a circle. We choose the center of the circle like this, and we choose a point on the circle, which is point P, point on circle. So this means this is x, this is y, right? So now we can immediately say this is r. So we have a point, but now we have to say that this point is always on the circle. How do I do that? Well, we know that if I introduce an angle theta, right? So in geometry we have the notion of angles, and we talked about pi as a total thing. So if I keep r fixed, right? Keep r fixed, vary theta, right? So if I keep r fixed, vary theta, then I move along the circle, right? So but now we use the simple idea of the next step is use the idea of, my assumption is these things are already known. I'm just refreshing and reminding you of what they are, right? So the idea of trigonometry is that this opening thing, which is theta, it is convenient to replace theta by a function of theta, okay? So this is a very powerful idea. So you're saying that instead of talking about theta, I will use a function of theta. Angle theta replaced by a function. And this function of theta tells you, you see, this angle depends on, it's a right angle triangle. This angle depends on x and y, right? So what you say is that this is specific to triangle, right angle. Right? So given a right angle triangle, we choose a function which encodes information about the triangle. And what you do is the following. What you do is you write cosine theta is x over r, and sine theta is y over r. Right? So once this is done, then we know that if we keep r fixed and if we vary theta, we are moving on the circle. Just geometrically, r is fixed, it's like a string, and you just move like this, and that gives you the circle. So let us now follow this thing through. From this equation, we find that x is equal to r cosine theta, y is equal to r sine theta, then x squared plus y squared is r squared sine squared theta plus cos squared theta, which is equal to r squared, right? Because x squared plus y squared from Pythagoras is r squared, so you get a result that this thing, these functions have to have the property that sine squared theta plus cos squared theta has to be equal to 1, right? So this elementary result, right, very simple result, is very easy to understand from the geometry. But again, it has this powerful idea of replacing one object by a function of that object. That's a big step, right? And it turns out that in order to describe this triangle, this seems quite natural, but these functions have a very special property. These functions depend on theta, but they are very special functions. They have the property of being periodic. So that means that these functions, this sine, cosine, these are periodic functions. What does that mean? That means that if I replace theta to theta plus 2 pi, no change. Right. Geometrically, what it means is if I have this point P, it is theta, then I go around, I keep going, I come back like this, I come back to the same point. So pictorially I can see if I have theta, I keep going 2 pi, and I'm back to the same point, right? So geometrically we see this thing is 2 pi, but the geometrical thing also tells you something else, that once you replace theta by 2 pi, what you've done is the point has wound once round the circle, but it can wind twice, it can wind n times. So it turns out that this winding number plays a very important role in a subject called topology, which we will discuss. So this step in trigonometry of replacing a function theta, a variable theta, by a function sine and cosine theta does two things. First, it introduces an idea of a periodic function, and secondly, it introduces the idea of winding, that you come back to the same point once, twice, n times, but you're coming back to the same point, right? But that information turns out to a physical significance. The physical phenomena in which the fact it has gone down twice or 3 times makes a big difference. Okay? So simple things have hidden in them all kinds of information, and if one quickly goes through these things, very often you overlook these insights which are present in the system. So what we have then is this notion of a function, a notion of a variable, and we know that these functions are constructed to capture the properties of the system in which we are interested. And in trigonometry, the functions introduced capture the property of a triangle and capture the fact that in a right-angled triangle, Pythagoras' theorem is valid. So those are the two things which are encoded in these particular functions. See, the power of algebra is enormous. See? And sometimes once you're using algebra, you do not really have to draw pictures anymore. And so for some people, that is a disturbing thing. Geometry is much more intuitive. If you, I was trying to motivate things by geometrical things, it's intuitive. But algebra is much more abstract. Once you've written algebraic objects down, you don't have to draw any pictures anymore, and you can just work away. And some people have summarized this problem or this different way of looking at the world using geometry or using algebra in a very beautiful way. Hermann Weyl, who loved geometry, he said that for the soul of every mathematical being, there is a struggle between the angel of geometry and the devil of algebra. So algebra is something which is powerful, but it does not give you the kind of joy for Hermann Weyl, which a geometrical argument would give him. So, for example, the winding number in the picture is a geometrical object, but in the algebra it is just a statement about theta being periodic, theta plus 2 pi n, where n is an integer, is the same. So we feel that this step we've taken now allows us to start exploring the world. So what we've done is we have stressed the idea of equality. We've stressed the fact that you use units in order to make contact with the real world. And we've stressed that the idea of symbols is crucial for analyzing the world. And the symbols lead to the idea of functions. And the functions with these conditions are really the backbone of everything, no matter how abstract or complicated. That is the structure of all of mathematics and all of civilization. Whether you're doing engineering or whether you're doing commerce, this is the bedrock. These are the few principles on which the whole structure rests. So the next step we'll take next time is to look at functions and introduce a completely different operation which only works on functions. So what does an operation mean? For the numbers, the operation means if I give you two numbers, there's an operation of adding. What does the operation do? If you give two numbers and carry out the operation of adding, you get another number. Or if you subtract, you get another number. If you multiply two numbers, you get a number. If you divide, then provided you're not dividing by 0, you get a number. So these are the operations of arithmetic, where you do add, subtract, multiply, and divide. For functions, there is a new operation which we will discuss next time.